So go ahead, Hutch, and we're looking forward to the topic today of the real cost of control valve ownership.
Thank you, Steve, and welcome everybody. Thank you for tuning in today. As Steve said, the valves play a critical role in irrigation system, and this presentation highlights ways that we can add value to farmers that will last for many years. Valves perform multiple functions in irrigation systems, naturally on-off or isolation. Often we want valves to control downstream pressure in irrigation systems. Sometimes we want them to control upstream pressure in irrigation systems and sustain pressure upstream. We also want them to relieve pressure if pressure gets too high. And in some cases, we want to regulate flow, not pressure, but we want them to regulate flow. Here are some examples of valve installations at pivot points to turn pivots on and off, control pressure, at end guns on pivots to control the end gun in the corners, on big guns, on solid set or portable big gun systems, often controlled by wireless twig systems, downstream of filter assemblies to sustain pressure upstream so that when those filters backflush, there's sufficient pressure and flow for them to backflush correctly. Downstream of pumps on a branch to relieve pressure if necessary. A pump control valve could be on-off, or it could be sustaining or flow control to fill a system slowly. And then we have valve control for sprinkler blocks or drip blocks. So valves have costs in irrigation systems, and those costs can be obviously the direct purchase cost. There are annual operating costs with valves, and we'll go into those. And those operating costs can be the cost of energy, the cost of inaccuracy, which affects uniformity, and the cost of maintenance. So these are some of the things that we'll talk about today. Here's an example system. We have a pump on the left-hand side and a pivot on the right-hand side. The pivot could be a pivot, or it could be a block of orchard sprinklers, or it could be a big gun. We've got some elevation, which is shown by the ground profile, and the blue line represents the hydraulic grade line. And we've got a valve in that pipeline. And in this particular case, the pressure loss through the valve is fairly small, and so the annual cost of energy of that valve is small. Here's exactly the same system with a different valve that has a high pressure loss, and you can see that the pump has to work to a much higher pressure. And so there is a high friction loss through that valve, and there is a high energy cost associated with that because the pump is operating at a higher pressure. That pressure loss through the valve can have a number of forms. The most common is friction loss, but sometimes the pressure loss through a valve is the required pressure differential. Some valves require a significant difference between upstream and downstream pressure in order to carry out the desired function correctly. This is an animation on the types of hydraulic valve. It helps for us to understand the different style of valve when we're thinking about friction loss and accuracy and performance. A lot of valves that are available on the market today are called bonnet-style valves or weir-style valves. They have a rubber diaphragm that operates on a seat. And as the flow goes through that valve, the diaphragm lifts up if the pressure is relieved from the top of the diaphragm and flow goes through. The control can be difficult because the diaphragm has to seal on quite a large ring of surface area. And particularly if fine adjustments in pressure are required, control can be difficult. The water has to change direction through this type of valve multiple times, and this causes turbulence, and it results in high friction loss. The Nelson valve, on the other hand, has a straight through flow. It flows straight through the valve, minimal turbulence, and minimal friction loss. The Nelson valve has instead of a diaphragm, it has a rubber sleeve, and that rubber sleeve contracts onto and expands away from a cage. As it expands away from the cage, it lets water flow through slots, and those slots have a specific shape and design. And as the sleeve expands further away from that cage, more surface area, open surface area, is exposed to the flow, and the valve passes more water. The design of those slots allows very precise pressure control, particularly if the flow through the valve is slow and the pressure reduction required is high. So that gives you an idea of how the different style valves work. A few years ago, the Irrigation Training and Research Center in Cal Poly in California did a test on a number of different valves that were available in the market. And you can see that the friction loss through those valves was quite different. 4-inch valves are quite common as zone control valves in California, so that was the size of valve that was picked. And you can see there's a dramatic difference in friction loss between those valves. The ITRC also looked at how well these valves regulated pressure. And here is a graph from that study, and you can see that in this particular case, the target downstream pressure was 13 psi, but the valve really didn't start regulating until the inlet pressure reached 20 psi, and then it regulated at 15 psi, not the target 13 psi. And due to hysteresis, the downstream valve pressure could be anywhere between the red line and the blue line on that graph. And we often hear from designers that they will allow 5 to 8 psi more than what is required in their designs, just so the valves have enough pressure differential to carry out their operation correctly. So the question becomes, how does all this affect farming costs, and what is the effect to the grower? So here's an example design. It's 100 acres of drip, and I've split it into 8 blocks. Each block has a valve, a control valve, and the flow through each valve is 290 gallons a minute. And the required pressure downstream of the valve is 11 psi. So if for example, that farmer is applying 24 inches of water per year, this is the effect of the additional pressure required if the valve needs more pressure to actually function than is what is really required. So you can see if a designer sets a required pressure above what is required of 5 psi, that valve is going to consume $40 worth of electricity more a year per valve. And on a farm basis for that whole farm, we can see that for 24 inches, it's just over $300 per year in additional energy required to operate that system. And the main message here is that economic valves that don't perform as well, or cheaper valves that don't perform as well, can become very expensive over time. Let's go back to this graph showing the hysteresis, and this demonstrates the inability to accurately and consistently deliver the required downstream pressure to a valve. And if we translate that to our irrigation project, what I've done here is put in various pressures that represent hysteresis and the inaccuracy and inconsistency from one irrigation to the next of delivering the required downstream pressure. So instead of 11 psi, we have a range of 11 to 14, and those valves may arrive at different settings between different irrigations. This is the block uniformity that was targeted. The system was designed for a downstream pressure of 11 psi, and the resulting EU is 92. And EU is the same as DU, except the coefficient of manufacturing variability has been factored into it. So this uses a good quality drip tape with a low variation of manufacturing uniformity, and the EU is fairly high. The pressure variation is in the order of maximum almost 10, minimum just over 6, and so you can see the variations. But that all arrives at an EU of 92. If we take into account the hysteresis and variability of block pressures in that project, we get a very different picture. On the left side is what we designed to, but on the right side is what is actually happening. Valve pressures range from 9 to 14. The maximum emitter pressure on that whole farm is well over 13. The minimum emitter pressure is about 5.5. And we can see that the EU has dropped considerably to 87. The variation in pressure about the average is 95, and the variation about the inlet pressure is 81. So poor pressure regulation results in higher energy costs, pumps operating away from intended duty points, over and under watering of various blocks within a farm, lower whole farm uniformity, lower crop uniformity, and lower crop productivity. And a system may be designed really effectively, but if there's poor pressure regulation, it really is equivalent to installing a poor drip irrigation project on the farm, drip irrigation product. To highlight the importance of what pilots do, here is the schematic, and the pilot is controlling the downstream pressure. In this case, the downstream pressure is a little high, so the valve is taking water from the upstream port and putting it on the sleeve to create a little bit more friction loss so that the downstream pressure comes back to normal. In this case, the downstream pressure may be a little high, so the pilot has detected this and rearranged the ports, and now it is taking water off the sleeve and venting it to atmosphere, so a little bit more pressure can get through the valve and control the downstream pressure. So we can see that the function of the pilot is extremely important, and the way it ports the water controls whether the valve is creating more or less pressure loss. The Nelson pilot has some significant advantages in doing this. Possibly one of the major ones is that we have quite a large diaphragm diameter. And the diaphragm diameter and the corresponding spring strength really work together and are easily able to overcome breakaway friction or friction of motion as this spindle or spool works in and out of the bushing that controls where the water is ported to. So the diameter of the diaphragm and the spring force are much greater in comparison to any friction, so they're much more able to deliver a smooth operation of the pilot. The geometry of the spindle and the geometry of the bushing and how the O-rings are held also mean that has to move in a minimal amount of travel in order to port water to the direct orifice. So if the movement of the spindle is minimal in order to change how the valve reacts, then it's going to be a lot more accurate. The other things that come into play are that the materials are high quality materials. The surface finish on those materials is of a very high quality, which eliminates friction. Some competitors will put oil lubricants into this spool assembly. And while that may help when the pilot is new, that lubricant often gets washed away, or if not, it is contaminated by sediment, and then the accuracy of the pilot really goes downhill from then on. So really, in summary, it's the combination of the valve design and the pilot that deliver the low pressure loss and the accurate control of the Nelson valves. And we have control valves in the field for over 20 years. And so they've paid for themselves many times over in terms of pressure saving and an accuracy of control and uniformity in the field. So that's a fairly short resume of accuracy and the importance and the effect on irrigation systems and crop production. Back to you, Steve.
Well, thank you, Hutch, for doing that. I would invite anybody that's attending today, if you've got any questions at all, please send those. There'll be a question and answers spot on your webinar or your Zoom webinar screen. So you can click on that and send me any additional questions. I've got a few here. But Graham, you do such a good job of presenting this topic. And it's so important to know how our valve sizing impacts the designs that we do and the uniformity in the end product, because the growers invest a lot in these whole systems, but really the heart of this, maybe not the heart, it would be the pump perhaps, but these valves are so important to the accuracy of the whole overall system. And like you said, in the example of a drip system or high quality sprinklers, any of these emission points, we get a very high quality emission point, but then if we don't valve it correctly, just like sizing our pipes incorrectly, it can affect the entire system. So I've got a couple of questions for you, Hutch, and for Evan. Evan, so thank you for being part of the panel today. Also, here's a question that was sent in, and please continue to send your questions. We've got time for a question or two more, I think. So question number one, where can I find friction loss data for Nelson irrigation control valves? I'll just go ahead and answer that one. It's at nelsonirrigation.com. You'll see the website address and on your slide there. So nelsonirrigation.com will have updated information and friction loss and that type of thing. And a lot of helps there in getting you to size the valves correctly and do some of those calculations. And if you need help in knowing what your sort of what the overall costs are and you want to revisit that or into these other topics, this webinar is being recorded. You'll be able to watch it again and revisit the topics that Hutch has covered. And you'll see there on your screen where you can watch this and other webinars.
Steve, just to add to that, and we do have information for valves with valve adapters too. For example, 3-inch adapters with 2-inch valves, 4-inch adapters with 3-inch valves, 6-inch adapters with 4-inch valves, that sort of thing.
Well, that's a really actually excellent segue into our next question is, if I have a 6-inch pipe, do I use a 6-inch valve? How would you respond to that?
It really depends what you want that valve to do. If it's straight on off, you could use a 6-inch valve very easily. If you want to minimize friction loss, 6-inch valve very easily. But if you really want to control pressure and you've got a significant variation in flow that might go through that pipe, often a smaller valve will give you much more precise control. And that's where some of our adapter assemblies can really help you, because for example, our 646 valve assembly will fit between 6-inch flanges really well.
Okay, good. So the valves really are sized by flow rate and the kinds of things that we're asking of it, and then we're just fitting it into a pipe.
Right.
Another question, does the orientation of the valve affect pressure control? So if we've got it side horizontal or vertical, does that affect the pressure control of the valve?
No, it doesn't, and we often have, most valves are installed horizontally, but we do have valves installed underneath our big guns that are vertically oriented, and they have pressure control and they work really well.
So another question, how can I prevent water hammer in my system?
That's a good question, and it's a big topic. But keeping velocities low is a primary um, goal in designing a system to prevent water hammer. And the velocity and the distance that the water has to travel are significant factors in the water hammer calculations. Um, Pressure relief has to be of a certain nature. Standard relief valves may not act fast enough. You will need surge anticipating valves to detect the downstream, the low pressure wave when water hammer occurs, and be open when the high pressure wave comes back. But preventing is really design in the pipe work and keeping velocities down.
We've got air vents. That's another type of air venting.
Getting air out of the system is critical. Good point, Steve. Yeah.
Yeah. Well, and we don't often or don't always think about how much mass there is in an agricultural pipeline. And, we're taught in irrigation design classes that we can move this water at up to 5 feet per second, but maybe slowing down a pipeline full of water traveling at that, if it's a 12-inch pipeline and we've got a 8-inch valve in it, slowing that water down uh, needs to happen slowly. So the valve opening and closing speeds will have a big impact of that in water air vents. So does air in the system affect the operating economics? That's another good question.
It really does, because if you've got pockets of air in a system, you really create a pipe that is operating, let's say, at half or two-thirds full. And so you may have an 8-inch pipe, but at a high point, if that 8-inch pipe is half full of air or two-thirds full of air, effectively you're creating quite a bit of friction loss. And it's worthwhile noting that air pockets can move, and they can move fairly rapidly. And so going back to your point on water hammer, Steve, if air is not relieved at those points and it has opportunity to move, it can cause damage apart from the additional friction loss that it creates.
So, Graham, what would you or Evan, you can feel free to chime in here too. In some of the areas, Graham, that you go, or Evan, where you have helped people in sizing their valves, the cost of electricity and the hours a year that they will run that system will have a big difference on its economics. Is that correct? I mean, so here in the Pacific Northwest, we pay very little for electricity, but I mean, how quickly does that curve change? So, I mean, if you go from, in your example, Hutch, the math was based on 10 cents per hour per kilowatt hour for electricity. Um, how quickly does that amount, like, is it exponentially that the cost of power plus the hours that we run that system, how quickly does that change the economics?
Well, it does change the economics, and as you say, in the Northwest, electricity can be more economic, 6 or 7 cents a kilowatt hour. In some countries in Latin America, it's 25 cents per kilowatt hour. So if the cost per kilowatt hour is 3 times as much, then the cost of friction loss is 3 times as high. But I think it's important to also mention that in irrigation, pressure is your friend. And so while there's a cost to it, you really want to deliver as much pressure as possible to the final emission device. And so if it's a pivot, the goal is to get as much pressure to the sprinkler as possible while minimizing the pressure at the pump. Or if it's a block of drip, make sure that the drip has adequate pressure to work correctly, but minimize the losses in the system so that the energy at the pump doesn't cost the farmer more than it needs to. So friction loss along the way is your enemy. Pressure at the end is your friend. Pressure at the pump is what costs you.
So, Evan, a question for you. with your engineering background and a lot of the irrigation design experience that you've seen in the design of these piping networks, where there's multiple valves in a manifold, how might the design of and sort of construction of somebody's irrigation manifold affect their economics when they may be putting in things like water meters or fertilizer injectors? Is there impacts on economics or?
Yeah, it's a good question, Steve. I mean, certainly the way you design that manifold and whether or not you're using the proper amount of distance between flow meter and check valves and your regulation valves, all of that can come into play in how stable your system is and how accurately it will regulate pressure. And so, often people will think, well, if the flow meter, I got to have, two pipe diameters upstream and one down or something like that. But they think on a pressure regulating valve, it's okay to put that valve, right next to the check valve. And what that can do is create extra turbulence in the valve, and it'll have a harder time accurately regulating pressure. So what can happen then is the valve could start to hunt or cycle. And if you have a VFD on the system, it's going to respond in turn to the cycling that the valve is seeing. And so what you thought you had a nice economic system that was going to be, stable, now you're going to get, wild pressure swings and not the stable energy consumption that you think you're going to get. So yeah, certainly how you design the headworks and the rest of the system can play a part on that overall economics.
And like you said, knowing the stability that can affect a lot of other things. Their fertilizer injectors, their water meters, the types of things that so they know how well they're doing. Whether you're putting the water into a pivot or a drip system. Here's another question. How as far as like I think this one's probably affecting the design of those pressure control pilots. Hutch, you showed us a lot of information on how important it is in the internal design of the pressure control valve. The pressure regulating control pilot is very important. Um, so what about filtration? How does filtration affect that? And what, if you were designing a drip irrigation system, speak to filtration as far as the pressure control pilot goes.
I guess that one, that's a system that has a fairly high degree of filtration anyway, Steve. So I think the pilots would survive really well under those conditions. And we have filters on our valves so that the orifices in the pilots are free of sediment. We do offer an internal filter or an external filter with more surface area. So if it's in an irrigation system that doesn't need a high level of filtration, like a big gun system or a pivot irrigation system, and the water does have sediment or organic debris in it, the external filter may be a very good option just to make sure that the filter doesn't get plugged too frequently and is easy to clean, and the pilot can continue to operate well.
And then as far as the winterization of these control valves go, that's not really an economic consideration, but maybe it is over time, easily being able to winterize this type of a control valve. Evan, you have published information on winterization of the control valves. How difficult is that to do in these different types of filters that Hutch has mentioned?
Yeah, it's really pretty easy. I mean, an external filter is it's critical that it gets winterized, and it has a really simple flush valve on the end of it. So if you just open that flush valve for the winter and drain it out, you'll protect that external filter. But certainly any other components that are on the valve, especially solenoids, are sensitive to freezing. And so, yeah, I mean, it's maybe not your, day-to-day economic costs, but your annual costs are going to be there if you have to replace every solenoid every year because you forget to winterize things. So certainly blowing all the tubes out doesn't take an air compressor. That certainly makes it easier, but you can you can blow it out manually, just by, blowing through a straw essentially. So yeah, winterization is also important to the economics.
So, Graham and Evan, thank you very much for presenting today. Hutch, that's excellent information. I think that this type of thing from a designer's perspective, from a grower's perspective, but mostly, maybe from the salesman's perspective, it allows, gives people information that they need to be able to sell up to Nelson irrigation control valves. Why having this level of accuracy in your pressure control pilot matters. The rugged stability over time of the 800 series control valves and the new innovations that are coming along there. As far as the aluminum cages and the weight savings, there's been so many great innovations, but it all comes down to not just buying the valve one time, but the fact that it's going to be there operating for decades.